All right, welcome. In this video, we're going to be doing two things. First of all, we're going to be reviewing some of the basics of the electric field, and then second, we're going to be doing an example problem, finding the net electric field in 2 dimensions. So let's get started with the basics of the electric field. All right, so far what we know is that if I have 2 positive charges, these 2 positive charges are going to exert forces on one another that are going to be repulsive forces. So they're going to push these 2 charges away from one another. And if I have 1 positive charge and 1 negative charge, then these are going to exert attractive forces, and these 2 charges are going to be attracted towards one another. Now, if you begin asking the question why, right, how is this possible? How is it possible that these 2 particles that have this property that we call charge are able to exert forces on one another, and specifically, how are we going to explain how they can exert these forces at a distance, right, without touching each other? Then we get to this concept of the electric field. All right, so the electric field is a way for us to map out, think about how the charges exert forces on one another, even if there isn't necessarily another charge present. So normally the way that we think about this is by starting with a positive charge, and then we're putting another smaller, much smaller positive charge in the area, right? And we usually refer to this as a test charge. We're saying we're just going to test out what the direction of that force would be, and as we said before, we know that that's going to be repulsive. And if I start adding more and more of these little test charges, these positive test charges, I can get this set of vectors that are all pointing away from my positive charge. Now, if I take this to an extreme, I can end up saying that if the test charge has an actual size of 0, or we get rid of that charge altogether, what we're going to have left is the electric field. All right, so that's where this definition that we can see of the electric field at a particular point in space, right, we're identifying its location in terms of its x, y, and z coordinates, is equal to the force on that charge at that same location, right, divided by the magnitude of that charge. All right, so oftentimes you'll see this written as the force equals the charge times the electric field. All right, so there's one charge that's creating the electric field, right? So in this case, this charge here is the source charge. It's creating the electric field, and then there's this other charge that would be experiencing the force, but ultimately we divide that force, or divide that charge out of the force, and we're left with an electric field. The other thing that we can see from this is that the electric field for a positive charge is pointing away from that charge, right? So the electric field is pointing away from the charge. Right, my source charge that's in the center here. The exact opposite is going to be true for a negative charge. So if I've got a negative charge, and again I'm going to use this small test charge, positive test charge, to see the direction of the force, right? But if it's small enough, then we just get the value for the electric field. I'm going to get a series of vectors that are all pointing towards my negative charge. And so in this case, my electric field is pointing towards my source charge, Q. All right, so the last thing that we can say is that the electric field for a point charge, and in this case we're just talking about the magnitude, again that direction's coming from whether that charge is positive or negative, telling us whether it's pointing towards or away from the charge, but the magnitude of it we can say is K, our constant, 8.99 times 10 to the 9th, times Q, our source charge. Again, this is my source charge. all divided by the distance between the source charge and whatever position we happen to be looking at, and we're noting that with the same variable as before, r, and that's going to give us our distance. All right, so with these basics in mind, we can start looking at this example problem. Right, so in my example problem, I'm looking for the strength and direction of the electric field at the position indicated by the dot in the figure. So the dot in the figure right over here, and we're specifying the direction as an angle above or below the horizontal. All right, so again, I'm just going to remind us that the electric field, the magnitude of that electric field is going to be that kq over r squared, where r squared is the distance between the charge and the point where we're looking for that electric field. So in a diagram, or in this diagram, I can add in the distances r right here and here. Right, and these distances are the hypotenuse of right triangles, where the two legs of both of these triangles are going to be 5 centimeters. So r, using the Pythagorean theorem, is the square root of 5 centimeters squared. So let's convert that. 5 centimeters squared plus 5 centimeters squared. And that will give us our total distance, r. So what I'd like you to do right now is, just looking at this problem so far, what can you say about the relative magnitude or size of the electric field at this point, at my dot, from the individual forces on my positive Q1 and positive Q2. All right, so I'd recommend pausing the video for a second and thinking about what the relative size of these two electric fields will be. All right, so hopefully you've come up with the answer that the electric field, the magnitude of the electric field from both 1 and 2 are the same, right? And if you haven't, let's take a look at why. All right, so the electric field for charge 1, Q1, is going to be k Q1 over r squared, and for 2, it's going to be k absolute value of Q2 over r squared. These two r distances are the same. The magnitude, right, the absolute value of Q1 and Q2 are also going to be the same, and so the magnitude of the electric field from Q1 and the electric field from Q2 are going to be the same size. Now what that doesn't mean is that I can just double one of these to get my final answer, because the electric field, just like the force, is going to be a vector, and so we need to include the direction of those vectors. Now, usually when we're doing the force problems, we would do a free body diagram. Now, technically, free body diagrams are used for forces, but we can do something similar to look at the electric fields at this point. So I'm going to draw the point on my page, and I can draw on that point the individual electric fields. So first of all, for Q1, I've got a positive charge, and what we said before was that positive charges have electric fields that point away from our source charge, right, away from the charge that's creating the electric field. And so my electric field for 1 is going to be pointing away from Q1. And then we can do the same thing for Q2. Right? The electric field points towards negative charges, and so I can draw my electric field for 2, which is going to be pointing towards Q2. All right, so we've got a analog to our free body diagram with the electric field, and it looks something like this. All right, so if I want to fill this in the rest of the way, I can say that the system for this is Q1 and Q2. I'm looking at both of those electric fields, and I can add in my coordinate system as well. All right, so once again, I need to know something about the direction. which means I need some sort of angle. And we aren't explicitly given any angles, but we can find them. And there's a couple different ways that we can do this. One of the ways is using inverse trig functions. We know all the sides of the triangle, so we can really pick any one that we want, but it's actually going to be a little bit simpler than that because these two different triangles that I have, right, are both going to be isosceles triangles. Specifically isosceles right triangles, and so what that's going to tell me is that the other angles of my triangle are going to be 45 degrees. Alright, so I'm going to have 45-degree angles here and here. That also is going to tell me that I have 45-degree angles here and here on my, again, free body diagram analog. Forces are going to continue in this direction. And so I can, in a multitude of different ways, show that those two forces are going to be at 45-degree angles. All right, so we're looking for the net force in the x and y direction as we did net electric field in the x and y direction, just as we did with the force. All right, so the electric field, the net electric field in the x direction is just going to be the sum of the electric fields in the x direction. And so that is going to be a positive electric field from Q1, right? Positive because it's directed to the right, times the cosine of theta, because I'm looking for that adjacent component to get the x component. And then I'm going to subtract from that the electric field from Q2 times the cosine of theta. Now, what we had mentioned before, and I'll write this down, is that the electric field, the magnitude of the electric field from 1 is equal to the magnitude of the electric field from Q2. And so, in this particular case, these two x components are actually going to cancel out. So the net electric field in the x direction is going to be equal to 0. But we will look in a minute what would happen if I didn't have those cancel out and how I'd finish this problem. But for right now, let's look at the y direction. All right, so the net force in the y direction, the net electric field in the y direction is going to be the sum of the electric fields in the y direction. And so this will be a negative electric field from Q1 times the sine of theta minus the electric field from Q2 times the sine of theta. All right, so sine of theta getting me that y component, and then they're both negative because the y components are both pointing down. All right, so I can write this out a little bit more thoroughly. Right, or we can just swap out Q1 for Q2 because the absolute value of Q1 is equal to Q2. And so I can say that the net force, the net electric field will be given by this equation. All right, this is technically the magnitude and the direction, so I could take the absolute value of this, and this would give me the magnitude. The problem does ask for the direction as an angle above or below the horizontal. And so since this is entirely in the y direction, I could say that the direction is 90 degrees below the horizontal. All right, and once again, I'll leave the calculations of this to you all, mostly because I do not own a calculator. All right, the last thing that I want to talk about is what would happen if I didn't have the same magnitude in the x direction. So if my x directions didn't cancel out, how would I finish this problem? All right, we can have seen examples of this before, but let's just see it one more time. So maybe I have the exact same setup, so I'll be a little bit sparse on the details. But instead of Q1 I'm going to have twice that. So this will be 2 times Q1, and this will still be Q2. All right, so all I'm doing here is I've got a positive charge that I'm doubling, but all of the distances are going to stay the same, right? So my R value for each of these is still going to be the same. The angles are still going to be the same. All right, so I would get my free body diagram analog, and it might look something like this. Right, where the magnitude of the electric field for Q1 has doubled because the magnitude of my charge has doubled. All right, so I'm going to get the same equations, it's just that the x direction isn't going to cancel out, so I'm going to write those out really quickly. Now I've left each of these in terms of Q1 and Q2 because we're holding on to this idea that the absolute value of Q1 is equal to the absolute value of Q2. And this is going to allow us to simplify this. So I'm going to put each of these in terms of Q1. So this Q2 in both of these I'm going to replace with my variable Q1 because it's the same magnitude. And so then this is going to allow me to simplify both of these. Alright, so I've got a bit in the positive x direction and a lot in the negative y direction. Alright, so my net force is going to have a little bit in the x direction and a lot in the y direction. So I can use that head to tail summation to find my net electric field vector. So I can start drawing my net electric field in the y direction from the head of the net electric field in the x direction. And then my net force will go from the tail of the x direction to the head of my y direction. Okay, so this tells me two things. I've got a right triangle, and so to find the net electric field, I can use the Pythagorean theorem. And then to find my angle, which we'll call phi, not to be confused with theta, which is the 45 degrees, I can use the inverse tangent. All right, so again, a lot of this should be looking really familiar because for the most part, we're going through the exact same process that we did when we were doing this for the forces, the electric forces in 2 dimensions. So I'm really going through this problem again, mostly to give us another chance to see that process if we need to see it again. All right, so let me know if you have any questions, and good luck.